Greetings everyone, it's an honor to present our work titled Feature Perturbation, a Panacea to Enhance Transferability Estimation. This study represents a collaborative effort between the researchers from IIT Delhi and University of Queensland. I am Praful Kumar Khoba and I had a privilege of working on this research as a part of my doctoral studies. Joining me in this collaborative effort are Dr. Zhijian Wang from University of Queensland, Dr. Chetan Arora from IIT Delhi and Dr. Mohasab Bakhtash Mullag from University of Queensland. This research will be presented at WACV 2025 and we are excited to share our findings with the community. Let's begin with the common challenge in the field of transfer learning. Imagine you have a pool of pre-trained models. The question is, which model you should choose for your task? Selecting the optimal model is crucial, but it comes with its own set of challenges. One solution is to fine tune each module on the target task. However, this is both time consuming and computationally expensive, especially when dealing with large pool of models. This brings us to an alternative, that is transferability estimation metric. These metrics provide a faster way to predict how well a model will perform on a target task without excessive fine tuning. Our research builds on this idea and addresses its limitation by introducing a robust enhancement to these metrics. Let's dive into it and how we achieve this. Let us discuss the limitation of existing method and how our approach addresses these challenges. Existing method primarily focus on adaptability. The core idea behind many of these metrics is to establish a statistical relation between the feature embedding of the pre-trained models and the labels of the sample, thereby generating a transferability score for each metric. Based on the score, these metrics aim to predict the actual rank of these models on the target dataset with the goal of achieving a high correlation between the predicted rank and the actual rank. While this is important, these metrics overlook a crucial factor, that is robustness. Robustness evaluates how resilient the embedding are when exposed to change or disruption. Our contribution is a novel method that evaluates and enhances robustness through control perturbation of the feature space. This perturbation help us test whether the model embedding retain their structure and meaning under altered condition. The left plot shows initial embedding, the right plot shows embedding after perturbation is applied. Here, the clusters are expanded and boundaries between the classes are blurred. As traditional metric rely on adaptability of the features, they tend to produce lower transferability score post perturbation for all the models. Yet, the degree for score reduction varies significantly among the models. For instance, if one model scored drastically compared to the other, it indicates a lower robustness to the perturbation. This substantial decrease suggests that the model embeddings are overly sensitive to the change, potentially undermining its performance when applied to new target dataset. This leads to a more accurate relative ranking of these models. Recognizing that the embedding structure varies with the feature extractor and the target dataset, our method avoids a one-size-fits-all perturbation. Instead, it dynamically adjusts the perturbation magnitude to preserve the meaningful structure of the embedding. We achieve this through two operations called spread and attract, which are described below. The first operation in our methodology is spread operation. Its primary objective is to test the robustness of the embedding by increasing intra-class variability. As you can observe the equation, the original features are getting displaced unit direction away from the centroid. Notice how the initial compact cluster expand after the spread operation. This perturbation pushes examples that were previously near to cluster centroid and thus easier to classify further away, increasing their variability and making them more challenging to classify. The second operation in our methodology is attract operation. Its primary objective is to test the robustness of the embedding by reducing inter-class separability using the equation provided below. The spreaded features are further updated based on the centroid and the variance of the class. Here, alpha is the hyperparameter that modulates the magnitude of displacement toward the other class centroid. Sigma is the hyperparameter that adjusts the sensitivity of the displacement to the variability within the class embedding as measured by RU and RV, which is L2 norm of the variance of the class. After introducing our methodology, it is important to emphasize why control perturbation play a critical role in our framework for transferability estimation. Let us understand with this toy example. On the left, we see the original feature space without perturbation. In the center, the optimal level of perturbation is applied. This preserves a balance between the class separability and inter-class variability, maintaining the necessary structural integrity for accurate transferability estimation. On the right shows how suboptimal perturbation setting can result in excessive alteration, complicating the feature space and hindering transferability estimation. This slide illustrates the impact of our feature perturbation framework on four widely used metrics: NCTI, SFDA, log-ME, and GBC. These metrics were tested under four different settings: original with no perturbation, spread only, attract only, and spread and attract combined. The bar chart show the improvement in performance with each operation. The best is when both spread and attract are applied. Our experiments were designed to comprehensively evaluate the effectiveness of our feature perturbation framework across diverse fine-tuning strategies, dataset, and models. Here we utilize three different fine-tuning strategies. First one, vanilla fine-tuning, where we update all the parameters of the model. Second, last block fine-tuning, where we update only the last convolution block of the model. Linear fine-tuning means where we update only the linear final classifier of the models. Here we present the comprehensive result for our experiment using vanilla fine-tuning strategy using Kendall-Tau value. Higher the value, better it is. These metrics are evaluated with and without our spread tracked operation, as you can see in the table. On an average, our perturbation framework achieves an impressive 19.69% improvement over previous state-of-the-art metric. Looking deeper, the performance varied depending on the dataset characteristics. For challenging dataset like aircraft, the class conditional feature distribution overlaps significantly as shown in set A. This limits the effectiveness of the transferability estimation metric. With our method improving only 3 out of 5 metric, you can cross-check this observation with the aircraft column of the result table. In contrast, dataset with better separate features such as Caltech 101 and car set shown in set B see a consistent improvement. These slides present the result of our experiment with LBFT and LFT strategies. These strategies provide a more constrained adaptation of retrained model compared to vanilla fine-tuning under limited parameter updates. LFT results. In the table at the top, we observed that spread attract operation consistently improved the ranking accuracy of the metric across diverse datasets. LFT results. In the table at the bottom, we evaluate the linear fine-tuning strategy where only the linear classifier is updated. 3 out of 5 metric improved in this scenario. For a comprehensive analysis, including more experiment and evaluation, we encourage you to check out our paper. It provides detailed discussion, extended results, and additional insight of our framework. The introduction and evaluation of our feature perturbation mark a significant step forward in the field of transferability estimation. By integrating robustness testing through spread and attract operation, we not only enhance the accuracy of the existing metric but also introduce a critical dimension of resilience evaluation. This ensures that the ranked pre-trained model are not only performant but also robust to diverse and challenging target domains. Thank you all for your attention and interest in our work. For further detail, feel free to refer to our paper or reach out to us directly. Scan the QR code to access the GitHub repo. Thank you.